Hi everyone, I'm Fabio Tosi from the University of Bologna, and today I'm going to present ZipDepth, our approach to fast and generalizable monocular depth estimation. Monocular depth estimation takes a single RGB image and predicts how far away each pixel is. No LiDAR, no stereo camera, just one image. This is useful for robotics, augmented reality, and autonomous driving, where depth needs to be estimated quickly and directly from the camera. The challenge is a trade-off. Foundational models are accurate and generalize well across different environments, but they are large and computationally expensive. Lightweight models are much faster, but they are often trained on a limited domain and can fail when the scene changes. Our goal was to combine the best of both worlds, foundational model generalization with lightweight efficiency. Here you can see the problem. The foundational model produces a clean and accurate depth map, while the lightweight model is much faster but becomes unreliable outside its training domain. So, how do we close this gap? This is ZipDepth. It uses a compact encoder and decoder built from efficient blocks. During training, we used 3 parallel branches to improve the representation. At inference time, we fused them into a single convolution, keeping the final model fast and compact. We also use lightweight modules to capture additional context without relying on expensive self-attention. To improve generalization, we train ZipDepth by distilling knowledge from the foundational model Depth Anything v2. More specifically, we use the teacher's predictions on 14 million images across 17 different domains. This allows the student model to learn from a much broader variety of scenes that it could see from a single training domain. As a result, ZipDepth can handle challenging scenarios such as night scenes, underwater environments, reflective surfaces, and aerial views, without any fine-tuning. Across 5 zero-shot benchmarks, ZipDepth achieves competitive accuracy while using significantly fewer parameters and much less computation. There is also an important detail in the upsampling stage. Bilinear upsampling tends to blur object boundaries. Our convex upsampling preserves these boundaries and keeps the depth maps sharp, while adding very little computational cost. And this leads to our main result. Under the same setting, ZipDepth is 55 times smaller and 270 times cheaper to run than the teacher model, while achieving competitive accuracy. But efficiency is not only about the number of parameters. ZipDepth uses standard and deployment-friendly operations, so the model can be easily exported to different hardware without graph surgery. This means we can move from one platform to another without having to change or manually modify the network. This allows us to deploy ZipDepth in real time across a wide range of platforms, from a server GPU to an NVIDIA Jetson Orin and even an iPhone. As you can see, we reach real-time performance on all these devices, from 77 frames per second on the Orin up to 375 frames per second on an iPhone 12. Here you can see that ZipDepth produces consistent depth maps and achieves even better results than previous lightweight approaches such as light mono. But the real test is running it live. Here, ZipDepth is running directly on a regular iPhone 12. No cloud, no external GPU, just the camera and the model, running in real time. So, with ZipDepth, we bring the generalization of a large foundational model into a lightweight architecture that is efficient, easy to deploy, and fast enough for real-time applications, even on mobile devices. ZipDepth is fully open source, including the code, pre-trained weights, and the project page. Everything is available online, so you can try the model and reproduce our results. Thank you for your attention.